Okay, thank you. I would like to thank the organizing committee to invite me to speak here. And I'm not a statistician, I just do whatever. I'm a finance prof and specialize in risk management. And I work, in all kind of areas as long as it's relevant to the line of research I do. That's a credit risk. And as the affiliation suggests, I'm actually I'm an NUS professor in business school and also co-founder of a fintech company called Quiad. And this is a bit related to the company too. It's a sort of technique, data analytics is something I find tremendously useful for my line of work for both research and the company. So I spent a fair amount of time developing new techniques. So today I'm going to show you one. And actually years ago, about 2 years ago, 3 years ago I started. I didn't think it was possible, but I'm going to give it a try anyway. I think in principle will work, in reality may not, but to my surprise it actually worked, okay? So I'm going to share with you. And it's not just a sort of pure scientific talk, because the science behind it at some time is application. So there's a commercial product behind this. There's the techniques used to produce commercial product. Okay, so it's a variable selection problem. That's age-old problem in statistics or in machine learning, whatever. People may use different technology, different terminologies to describe it, but in essence, it's some sort of linear model or nonlinear model or sort of limited dependent variable, garden variety of those. It's basically we have many, many variables we had to deal with, and we want to predict something. We want to have a very good predictive power, out of sample, presumably, among the universe of potential explanatory variables. Given the tremendous increase in data, it's easy you can several hundred variables, even 1,000, or even get 100,000, 200,000 variables, and your observation will be limited, right? So you may just have several hundred. In the case I'm going to show you, actually I have over 141,000 observations, but I have 400 some variables. Okay, in any case, so long as a P, let me use the terminology people use N and P. P is the number of regressor or variables, N is the number of incidents or cases. So long as P is large, the problem is very complicated. Okay, now you say, why we need another technique on this? And it's because obvious reasons, so I'm going to share with you. Okay, so the talk is about variable selection with big data. So big data can be sort of N is big, could be P is big. N is big usually is not a big problem, it's a blessing in statistics, right? But a P is big is a curse. Okay, so I'm actually referring to P is big, but my data N is actually very big, and that creates computational problems too. Okay. Anyway, so the selection objective is zero norm, and you may not be familiar with this, and I will explain. Okay, and then I'm going to use a sequential Monte Carlo technique to do this. And some of you, because of Bayesian, you'll probably know sequential Monte Carlo technique. And here is, I'm not talking about filtering. I'm actually not talking about Bayesian statistics. And this has nothing to do with Bayesian statistics. It's a Bayesian computational technique for maximization. Okay. So let's start it. And so when you have NP is very big, you have no choice but use a regulated regression. In a linear model case, regulated linear regression, or in other cases, regulated anyway. Okay, so a bunch of variables here. So I'm going to use a least square to show you this, sort of motivate this example. Y is what you observe is a vector, and this can be n-dimensional, and x is np-dimensional. Beta is regression coefficient. That's typical regression model, and this is hopeless problem unless you regulate it, right? Regulating means to put some penalty. The most famous one is Lasso, and there's various variants or two Lasso now, okay? And so basically you try to minimize it just like you normally do, minimizing to get a beta regression coefficient. Without constraint, of course, that's an obvious solution, okay? But problem is x prime x can be sort of neo-singular, or it's just over-parameterized, too many variables, okay? So once you put the regularization here, means that you want the L1 norm to be less than t. So you basically want a coefficient, the absolute value, and sum of that to be less than some number. And that's where the regularization comes in. And that's the L1 penalty. Okay, this is well-known Lasso result. Okay, you may wonder why every beta is treated the same, but typically people will normalize x variable. So beta has the same meaning, okay? Or you can put a different weight there, but that's not the critical part of it. Okay, so anyway, this is a lasso, and a variance of that is just a different sort of penalty. Anyway, and you can formulate it as a Lagrangian problem. So basically what you have to do is just vary lambda to solve this problem. This is called tuning parameter. Then you have to find some technique to sort of find a tuning parameter. Typically people use a BIC, okay, or use a cross-validation, this kind of technique, okay, and to find the lambda. So basically you have to do this problem many times. This problem itself is very easy to solve. Initially people probably didn't figure it out, but later they find out to be they find out to be easy to solve because it's a convex optimization problem. And you can use the proximal gradient, okay, to deal with the non-differentiability of this L1 operator, okay? Anyway, so this is a sort of piece of cake running very fast, right, on computer. So this is why people use it, because it's very fast, okay? But now let me introduce what called zero norm. And instead of solving that problem with that penalty, now I'm going to change the penalty. Why is the PP is a maximum number of regressors in your data set, say 500. But you don't want a P500. You want some number which is smaller than 500. So that's where the penalty is. It basically say, I want to give myself maximum number of regressors, say 20 or 10. Then a tuning is something you have to vary that number, right? So like a tuning as well. But you see, this problem is an infinitely harder problem because this is actually a combinatory problem. Okay. And people call it zero norm. Actually, that's an abuse of terminology. It is David Donahoe called it the zero norm. This is no norm, actually. It doesn't have homogeneity at all. Right? It's basically count how many non-zeros. It's basically allow how many regressors, basically. Okay? That's the way you can think about zero norm. So it's just a standard terminology, but it makes no sense, okay? It's not a norm. Yeah. But anyway, people call it zero norm, so go for zero norm. And so if you start to solve this problem, you realize it's a very difficult problem. What I'm going to do is going to reformulate this problem into the following problem. Think about it, I'm minimizing this like I'm maximizing this. You notice that? Right? Because the basic regression, you think about it, this is almost like a likely function of the sum of residuals, right? Just the other way of saying. If a statistician starts with normality, they're formulating this problem, end up having that solutions, right? Okay. But the thing is, what are you going to solve, though? Without constraint, it's a simple problem. With a constraint, it's much harder because what you are constraining, in a way, if you formulate this way, you're formulating coming to search over random combinations. Suppose you allow your 7 regressors, random combinations. Now, if you have a 500 variable, you try to get a 20, 25 of them. You know the order of that is going to be 10 to the 40 or 10 to the 35. Okay? Machine will just quit. And I was told by computer scientists, 10 to the 12, supercomputer can do it. Okay? And get to this territory is just basically not possible, right? So this is a brute force solution to combinatorial problem. It's hopeless. But then I look at this problem and say, there is a way to solve this. Okay, and this is known to be NP-hard problem, but it can do stochastic approximation of this, and the solution is damn good. And basically saying is, I'm going to use Monte Carlo technique to solve this problem. Okay, how this come about? It's actually motivated by statistics, Bayesian statistics, because I've been working on Bayesian statistics for application for a while. I'm not a Bayesian, I just really I don't care, But a Bayesian computational technique is quite beautiful. But here I'm going to talk about it, and I'm going to revise it a bit. Okay, because the people are so hung up on something which create a problem. So let me show you. So this is, I hope you understand what I'm saying. It's basically a random vector, say 7-dimensional or 10-dimensional, depending on PS. Okay, and it's going to be in this universe of a permutation actually, because once you pick one, you cannot pick again. You're not 7, right? So it's basically actual pick over permutation, but what happened is the combination doesn't matter. In other words, first variable becomes second becomes 7. Doesn't make any difference. You see what I'm saying? It's a very unique problem, right? You think about it. Anyway, this is completely chip formulation. It's a completely equivalent, right? Okay, I hope you agree. But just that space is way too big for you to actually solve it, by brute force. Okay? But anyway, suppose I tell you number of particular sets. Suppose given a random vector, I know which regressor to use. That solution is completely obvious. It's an analytical solution, which is beautiful because I'm going to use that, yeah? Okay, so I'm going to use that. So in other words, I'm going to solve very simple, I'm going to solve very complicated combinatory problem. And yet, given that particular combination, objective function is quickly computed, yeah? And that's a key, right? Otherwise, it is going to be not doable, basically. Okay. So now zero norm versus L1 norm. So let's spend a little bit of time. And other than technical issue, you think about it, zero norm is most natural, intuitive. When you tell people, I want to choose variables, say, give me 10, give me 15. You know, when they ask statistical question, whether it should be 15 or 12, well, that's a different statistical question. But it's not by any L1 approximation of penalty, okay? But L1 norm, like Lasso, what it does is dramatically reduce the number of regressors. In other words, the regression coefficient by penalty, it goes down to 0. Now, you can also use the L2 norm, that's called rich regression. It doesn't penalize enough. In other words, still get a lot of non-zeros, okay? So L1, that's why it's popular. It's easy to compute. So here, it's no good. Why? Because it's not very intuitive, right? Just think about it. That's one. But the reason people use it is because it's highly efficient, the technique of solving this. Okay. Now, Tipshinani's Lasso, which is now really so popular now, it does not possess an oracle property. Because of penalty, you think about it, you penalize everything. So even a good regressor coefficient will be penalized downward or towards 0, right? So it loses an oracle property, means the sample go to infinity, they don't converge to right value. But that, to me, is not a very interesting question, actually. Lots of statisticians, friends of mine, they really spend their lifetime on this kind of stuff. And I don't find that to be very interesting. Because the n go to infinity, it's hypothetical. I'm such a practitioner. I say, stop, I'm not even interested to hear that. Okay? And it's going to be small, right? So it doesn't have oracle property. It's not. I don't really care. Right? Okay. But anyway, even you think about oracle property, it can still be fixed by something called adaptive lasso because of the weighting on that L1 norm, which plays the trick. It's actually individual variable weighting. That's if you are interested. It's basically going here. So you weight these things individually by individual elements. Okay? And that's a trick, basically. The weighting essentially becomes 0 when the variable coefficient is significant. You know what I'm saying? You can get that idea, okay? Okay, anyway, so now in other words, a problem is called irrepresentable condition. This is in Zhao and Yu. It basically says this fundamental L1 norm penalty has a problem. Because what it says is this. Suppose you have a true model, then you have a bunch of other variables, which is nothing to do with the model. That's essentially the situation we have, right? So bound to be so many of them are nothing to do with the model, but they just there. We don't know whether they are relevant. So if those variables can be represented in some way by the true variable, and you got a problem. You can see that it's a basic correlation problem, multi-collinearity problem. Okay? And you can have all kinds of problems. You come up with real results with Lasso. You can always do pathological cases on this. And I'm not interested in pathological cases. I tell you, we have been using Lasso, adaptive Lasso a lot. There's a lot of problems. Okay, the problem I want to sort of share with you, it is actually very straightforward to understand. Okay, you think about it, go back to that equation. Here's a Lasso problem. Think about it. This L2 norm, the minimization, that particular original target, itself is invariant to rotation because R squared doesn't change. But when you rotate it, what happened to the penalty? L1 penalty will change. So it's not invariant to rotation. You think about rotation, basically it's create independent one by rotating, create collinearity, right? But now here we're not purposely trying to do, I'm just telling you the reality of many data points. Vectors, they are highly correlated. That's just the nature of things. Like I do credit, measurement of liquidity, I can come up with 5 ways of measuring, or even more than that. But every one of them, sensible, they're correlated, highly correlated. So that's the nature of things. As a selection, you say, I want to pick among these 5 liquidity variables, just one of them. And the space is going to save for other variables in other dimensions. But if you do in Lasso, you know what? surprise, surprise. At first, when we got a result, I would say, we must have done something wrong. We check infinite number of times, which is an exaggeration, of course. We check many times, we were convinced or correct. But then we didn't quite figure out what was the reason, and later on I figured out the reason for it. It's basically this rotation problem. In other words, when you have a two very correlated variable, just think about it, they happen going to that space, both will be knocked out because it will create such high penalty. So, ideally you want intuitively say, I have two very correlated variables. In a selection, I want to just have one as opposed to two. Because the second one doesn't help. It helps a little bit because they're not perfectly correlated. But the penalty is so high, right? I'd rather have another variable. So I want to choose one, but not losing two though. The reality, I keep on losing two. You see what I'm trying to say? And that's so funny, and I realize that's because of rotation causing it. I can artificially rotate the x variable to create that problem. But reality is variable are given, right? So there's some sort of correlated structure. So that's no good. Now think about it, if I use the zero norm, what will happen? Out of these two, it's going to be one, because if you take two, then there's less room for other. You got that? So zero norm is the most natural, intuitive way, and here we'll solve that problem too, automatically. Okay? You don't have L2, L1 norm to mix up by the rotation problems. Okay? So that's intuitive what is happening here. Okay? So I'm not going to be talking about too much on technical aspect of this. But anyway, so now, supposedly I already convinced you zero norm is the way to go. But how can I solve that combinatorial problem? In fact, I argue now I have a general solution to all mixed integer and mixed integer programming problem. Because integer programming problem is basically a combinatorial problem in some sense. You can always formulate it in a way. Okay, so that's how I'm going to do it. I'm going to show you how it's done. Okay, so first we have to understand sequential Monte Carlo technique, because that's the technique I'm using to solve this problem. Okay, but this sequential Monte Carlo technique hinges on one thing, so I'm going to show you what I meant by this. I'm arguing, okay, every optimization problem can be formulated as a distribution or density function problem. Because think about this problem. This is positive. It's non-continuous because remember, we're looking for this discrete variable, okay? So it's going to be probability function. Why? Because when it's positive, it can always turn. What is missing is a norming constant. If it's continuous, it's going to be density function. Differentiable will be density function. So I'm interested in solving over this U. So the space is U, this random vector. The function itself here is not continuous. It's a probability function. Right? Except I do not know norming constant. So every problem, every optimization problem can be turned this way. This is a generic statement, every optimization problem. Do you agree? Make it positive. You minimize, make it maximize it. And you formulate, except you don't have a norming constant. So if you have a technique which can bypass norming constant, you're sort of partially home free, right? If a technique required to compute norming constant, you're doomed. Because you don't know the norming constant. Right? In this case, it's not even clear you have norming constant, because this is not a normal distribution function. Because remember, the space is about U, right? It's not an epsilon. Epsilon is normal. So norming constant is very complicated. Yeah? Yeah. So anyway, if you have a technique to solve the problem, it can maximize this, it can do this without knowing the norming constant, and you are home free. But of course, you have other sort of technical issues to address. Conceptually, you're home free. Okay? So what I'm talking about today is Bayesian computation, but non-Bayesian statistics, because I'm just talking about maximize something, right? But I'm using these kind of techniques to do it. Basically, SMC involves generating a sequence of Monte Carlo sample. Now we have expert here. You generate sample. Why you want to generate sample? You want to generate sample to be representing that target function. Remember that target function is either probability or density function. if somehow you manage to generate a sample to represent that, just like you generate standard normal, the sample, the maximum value, you do functional evaluation on that set of 1,000, and that is your approximation to the true maximum, correct? And what kind of accuracy you want? Oh, simple, right? You want more accurate, just do more. Right? You get a Monte Carlo result, right? Okay, so the trick is to represent, using sample to represent that function, that generic optimization, objective function. If you can do that, okay? So SMC is a technique to do that. So I'm going to do that, okay? The Bayesian posterior distribution is motivating example for this technique, sequential Monte Carlo. So I will show you what. The prior can be simulated by Monte Carlo, the posterior is not. That's how Bayesian statistics is formulated, right? MC, everything. Because you think about it, Bayesian, you have a posterior, you have a prior, you have a likelihood function. It's just prior is so far from posterior. That's a so-so problem, right? You want to find numerical technique to generate it. So here I'm going to take some idea, okay? But it's a non-statistical problem. So if you have a Bayesian, you have a prior to start. But here I'm non-Bayesian. I don't actually need prior. So I'm going to go back to talk about Bayesian statistics. And I think people using prior is very ill-informed. I tell you why, okay? And you may say, oh, what's going on? Because every time I chance to run into Bayesian statistician, in particular a paper, I ask them, how do you come up with a prior? Invariable, the prior, many people are very honest. They will tell you, oh, my prior is for computational reason, not belief. Okay, I have not run into a single person told me that prior is because of real belief. Okay, it's a computational need. So that's very funny, right? Think about it. It's not something you believe. I'm going to tell you today, you actually do not need prior. You can actually run this kind of technique. Okay, you can completely bypass it. Okay, anyway, so you have to use a density tempering technique. This is Demerel and sequential paper. I wrote a number of papers on this as well. So basically, you want to use a density tempering technique to do it. So it will become very clear later. Okay. So, but I want to first of all to show you this irrelevant constant problem. So if you do importance sampling, you have a sample. Importance sample basically a sample point are unequal weight. Because the target density function is not a generator, so create importance weight. But you have two ways of doing it. Directly with importance weight, the other one normalized importance weight. It does not make any difference. The reason theoretically this will go to 1. Okay? But the key is, if you miss a norming constant, it will not be 1. So therefore, you should divide. Divide is get rid of a norming constant. So in other words, you actually do not need to know norming constant, either numerator or denominator. All you have to do is just get a weight and normalize the probability, and you're done. If you actually know norming constant, it will turn out to be approximately equal to 1 anyway. Okay? So that's the sort of understanding you should have. So this is a technique to get rid of norming constant, basically. It's to simulate to get a sample without having to pay attention to norming constant. Well, I guess people know that in Bayesian statistics, right? That's why every time posterior proportional to something. Right? People actually know that, right? Okay. So anyway, that's a quick one. So we need to have a concept called effective sample size, because that's a critical, and in sequential Monte Carlo, people sort of know this well. That basically, if I have a sample of 1,000 points, it may not be actually 1,000, because when the weights are not equal, the sample quality is poor. You had to calculate. Equal weight is the best, right? So sample size effective will become smaller if not even. Okay, if you have one, people sort of know a peak likelihood situation. If 1 point carries so much weight, in essence, your sample 1,000 is just 1 point, because the ESS is going to be approaching 1. Okay, so in other words, you think you have a sample of 1,000, you actually do not have. So the technique, the trick is control ESS. Don't let ESS deteriorate. Suppose I use 1,000, I would say I don't let it slide below 500. So I had to use that as a control measure. Okay. So that's some background to remember. Okay, so density tempering technique is the following. Okay, suppose now I use a standard Bayesian framework. Suppose you are interested in posterior. Let's, for now, just think about gamma equal to 1. So this is basically Bayesian problem, right? Because posterior is a proportional to likelihood times the prior. But if we introduce something called artificially called initialization sample called I theta, I stick right in there. It doesn't change the problem. It's still the same problem. And so far, I haven't touched on density tempering. Well, this is density tempering. When gamma is 0, it back to original formulation. When gamma equal to 1, you see that gamma and 1, these will cancel each other. So gamma equal to 1 is precisely the target. With or without I theta, gamma equal to 1 is the target. So that's become design, right? Part of design. I tell you why this is important. If you are Bayesian, then you will typically start out with I theta to be P theta, so they cancel. So you density temper the likelihood. But that's a dumb idea. That's how actually I was doing that. I published a paper in 2016, and I was using that as well. I realized how dumb I was. Because you know why? Because the P theta is a very poor sampler. If it's not a poor sampler, you wouldn't do Bayesian statistics. Because the data is highly informative, means the posterior is so far from prior. And why do you want your prior to simulate? You should use I theta. And every time you change I theta, you only change the efficiency of the algorithm. You do not change the mathematical problem per se. Now, if I repeat it, suppose I do this dumb thing, okay? I use a prior, get a posterior. Then I say posterior is my prior. I do it again. Of course, a completely illegitimate Bayesian, right? Because I use the data twice. Right? So actually, the learning discovery, it cannot help your simulation. But here, if I do this simulation many, many times, next time I just get a previous result and plug in, because it's I theta. It doesn't change my belief. My belief stay fixed. So I'm decoupling belief from simulation. That's why if you ask a Bayesian, actually, if you don't believe me, go ask them. Honestly, they will tell you, why you picked up P theta? Because that's good for simulation. It's not a belief. Because they don't separate I theta and P theta. And it's a very little trick. I wrote it in a paper. Before that, 2 years ago, I didn't have that realization at all. I was just thinking like that's how it be done. I realized, well, I was really dumb. I was really dumb doing that. Okay? So I theta, it's just like any sort of important sampling. The support has to be big to contain the target. Right? And you can build all kind of constraint in there. Because I theta doesn't have to be subject to constraint. All you have to do is the numerator subject to constraint. It will give you 0 weight. It will disappear. Right? It's a beautiful way of doing it. Okay. Anyway. So you can still be a Bayesian. That's what you will be doing. So that will be a problem you will be doing. If you're not a Bayesian, just make this 1. Right? That's because of statistical belief, whether you're Bayesian or likelihood. But the technique itself is completely agnostic to it. Okay? And you can actually do from learning. In particular, we do sequential run all the time. We have a live system. We do that up to today. Next month, we'll recalibrate the system. We just use the current information on theta as I theta for next run. It's so much more efficient. Otherwise, I have to go back to prior to run the data. You can imagine, right? Okay, anyway. Okay, so that's something you should understand. So anyway, the gamma itself create a bridge from 0 to 1. 0 is how you started. You think about it, when gamma is 0, essentially, you have intermediate posterior. You abuse the terminology. That's a basic initialization sampler. And so you want to control this gamma to make sure the effective sample size does not degenerate. So think about it. The worst thing is that the weight are not even. So by low gamma, you can always even the weight. Correct? Yeah, gamma equals 0, it's 1. Okay, you can always, so you can steadfastly control this gamma. Self-adaptive control, so it's highly efficient. Right? My typical experience is ranging from like a 10, 15, no more than that. Step. So what I have to do is progressing instead of using importance way. I'm using incremental importance way, moving from gamma to the other. Because what happened is this. I have a technique moving the cloud of the particle representing the theta in this case, or any random variable. I'm moving it to the next location. That's not my eventual goal. And I would sort of move and move. So this process, of course, needs support boosting. Otherwise, that sample will degenerate. So periodically you have to reboost it. So you understand what I'm saying now very quickly. So what you need to do, so you have to do support boosting. So what happened is initialization sampling, okay, you do that. And when you start doing this, you find the next gamma, okay? So you had to do resampling, support boosting. What resampling do is even out the weight. So what happened at a point with 20% weight, you're going to show up many, many times. Then you have sample impoverishment. You know, number of distinct points just drop, right? Now, empirical support is shrinking. Even theoretical support is R. Empirical support can drop. Once you have a point or identical point, empirical support just drop, right? So what you need to do is replenish your support, empirical support. That's called support boosting. What you do is best is the metropolis Hastings technique. So what you have is this intermediate target, and you just use a proposal to do that. This is standard metropolis Hastings. Now the beauty of this, now you have a natural way of designing, because if you're at a gamma stage, you already have a sample of theta, say 1,000 points. It gives you a natural independent proposal, right? You just look at it and say, wow, in particular statistical problem, typical multivariate normality, I'm going to take that sample, I look at a multi-normal approximation, because the key to this technique, you must know the analytical form. So it's use a multivariate normal approximation. I don't even have to get a complete covariant structure. I can use a block, because I just want to have a reasonable good sampler and get some sort of acceptance probability, right? Okay, as opposed to typical MCMC, and you got a design problem there, right? Okay, now everybody knows it's a very not easy. Here, there's a natural independent proposal. Now, the other thing which is quite critical is this Markov kernel is there at it. If you throw in stationary distribution, and out is just stationary. So it completely bypass MCMC problem. Because MCMC problem requires burn-in. This does not require burn-in at all. Because remember, it basically simultaneously runs 1,000 Markov chain, but a chain without convergence. Because you start out with a stationary distribution, what to converge? Your goal is to boost the support. In other words, 500 point become 1,000 point, distinct point. So it's highly efficient, right? Because you don't have to run this endless chain and don't know when to stop. And people telling you burn-in technique, but it's still arbitrary, right? Problem specific. So here you don't. Your point is that this Markov kernel is going to create a stationary, because in is stationary, out is just stationary. Yeah? And so that's the beauty of this. So there's an independent proposal. And by the way, in the end, the sample you produce 1,000 are independent. As opposed to after burn-in, it's still dependent. It's a single chain. It's not a good idea. You should get multiple chain without convergence, without the need for convergence. That's what I mean. So these are how sequential Monte Carlo can do. Anyway, so you can just keep on doing this. Okay. So I already touched upon this, right? There are several advantages of using this SMC, even in statistical context, Bayesian statistical context. Okay, but I'm going to tell you another things. Okay, this is advantage of SMC over gradient-based methods. Because I'm not talking about statistics, I'm talking about maximizations, right? So look, my problem cannot be done by gradient methods because it's not differentiable. Okay? And also dimension is high, it's very difficult. Non-convex problem is very difficult. And this is a solution of multi-mode solution, right? Because it's mimicking entire distribution. No one say that that target function should have single mode because I'm mimicking that distribution. Okay? So the other things, this is also a discovery, accidental discovery. It's this a concept called K4 duplication in a paper of mine, okay? You know, I'm doing sort of systemic risk things, okay? K4 duplication. One day I realized, you know, I can use the SMC technique to easily boost the sample size. I will 8,000, I want to get to 2,000 is very easy. Why? Because all I have to do is just replicate that once, so I have 2,000. You say, well, you have done something really silly, because that 2,000 is 1,000. ESS is still 1,000. True enough. But I can do support boosting, just like I did previously. I turn into 2,000. Advantage of that is I bypass intermediate steps. It's like I'm working on delta equal to 1 directly. because I already have 1,000 pretty good points. You see what I'm saying? That's called K4 duplication. It's the simplest idea you can do. You can apply that to MCMC too. After burning, you can just increase the sample size. You can increase their independence quickly by doing that. Okay? So anyway, so there's a K4 duplication. You can easily to increase the sample size. I mentioned all this, that's what I'm using in these solutions, okay? I basically take that, let me recap what I do. That is the target I'm going to do. That's the target I'm trying to solve. I'm going to simulate this combination, random combination. I know they are bad. I'm going to move steadfastly to a final solution. In between, I'm going to do all this kind of stuff to improve them. And now, initial simulation, of course, you got to have an initialization sampler. How easy is that? You look at individual R-square, just one at a time, individual regressor. What's your explanatory power by yourself? You will determine the probability on this. Of course, that's not end solution because there is no joint effect. And that has a very decent initialization sampler. Right? The other trick is you cannot simulate combination. It's very costly. You can simulate permutation easily. If you simulate permutation, think about it. The function can be viewed as an over permutation. That set is bigger than combination. Right? Because you collapse different permutation in single combination. So I can view it over a set is over combinations, possible combinations. But I can also view it as over possible permutations. That's actually much easier to sample. Okay? Sort of a few tricks here and there. You know, it took me a while to actually get it going because it's complicated. Okay? But idea, I already sort of share with you idea. So this is completely coded, and the first coded in R now, I've been coded in Julia. And these things run very fast, okay? So while I continue to talk, I can just demonstrate to you how this works. And we have gone on sort of fancy stuff now using API. It's completely web-based. I figure this is the best way to protect intellectual property. Okay, here is a tool. So let me show you. And it's just web-based. You don't have to install. But behind this is the Julia language, okay, using API. So variable selection. So it tells you you can run regression with the intercept or without intercept. Because intercept, you can allow it, but it will be chosen whether it's part or not. Right? Intercept is a regressor too. And the interaction term, what does that mean? You know, this is actually very important. You know, economic finance, we typically have sort of 20, 30 variables we consider. But why did we get into hundreds? It's because interaction terms. Before financial crisis, after financial crisis, you know, those kind of stuff. So you very quickly, you get to several hundred variables if you consider interaction terms. In the past, interaction terms has always been factored in by intuition. That's how economists are good at it, you know, intuition. It's not by data analytics. Now I'm going to use data analytics, so I'm going to allow interaction terms, okay? So here's just a sample file. Now, I can choose to use a cross-validation. If you don't, we can use a BIC or AIC or generate that, you decide. Right? And use common random number because for repeated use, you can use a common random number to sort of see the result. But this is on the networks, cloud computing, right? So the network configuration, the timer, it can cause the result to be different because of random number. Okay? And this is each one is on parallel, it's on 8 workers, okay? So this, yeah, go ahead.
So do you all use the same initialization?
No, you can choose to be randomized or you control. Some people want to control so they can repeat the result, right? So you can actually control. Okay. So default to 8 workers on this. There's a house on the server. This server is not a fancy computer, it's a sort of modern desktop computer. Okay? And with a 4 sort of physical CPU cores, so 8 threads, right? So 8 workers, something like that, or maybe 12, I don't know. Minimum number of regressors, you start out with a 2. And the maximum 30, that's a range. You can play it and figure out. Cross-validation will self-determine when to stop. Okay? So anyway, so I need to have a data set so I can sort of, here I get a template, right? So I'm going to save a template. So again, I'm going to browse. This is put it into a download, I believe. So here's a sample. Okay, so I'm going to just give it a run to say I'm going to do cross-validation and running for the range of 2 to 30. Okay, that's the maximum range of the variable. And this data set has 11 variables, but after interaction terms, it become like a 78 or 80, something like that. Okay, so I'm going to have it run. Okay, so it's running. This will probably take 2 minutes or something to be done. 2 minutes. This can handle up to 1,000 P, okay? I haven't tried beyond that, but I tried 1,000. It's completely workable. And data number n is completely inconsequential except data preparation. Create interaction term take a long time, because there are a lot of regression, but data science is very large. But the whole algorithm is based on sufficient statistics. Once the data preparation is done, it has nothing to do with number of data points. It all depends on P. Okay? P is critical, number n is not. But number n will determine. Even the sum take a long time, right? Okay, so anyway, so it's running. So I'm going to just, it's about 2 minutes, it will be done. So let's just stay on the screen, instead go back to that. So then I'm going to explain to you now the usage, okay? And I haven't finished the simulation study yet. But I'm going to demonstrate to you it's a real usage is create something called proxy CDS curve. For most of you probably don't know what CDS, heard about CDS. Now CDS is, I'm talking about corporate CDS. It's basically the bond guarantee. One party is insurance, sell to the other. There are about no more than 500 CDS traded out there with some liquidity. Around the world, how many companies, exchange traded companies, is over 35,000. Why I mention this? Because if you want to use a CDS to do work, you are out of luck. Because the company you're interested does not have a traded CDS. You understand? So people are very happy to talk about CDS research, but applicability is actually very limited. So the objective is to create a way of predicting CDS value so that those without CDS, it's over 35,000 of them, can actually still have a very good value based on these 500. Okay? So what we're going to do is link in this CDS price on this 500 company over history of 15 years into some sort of variable we can have for every exchange traded company in the world. Financial statements, stock prices, and all that. Link it to them. So once I establish that relationship, I can then apply it to every one of them. This is not forecasting, it's prediction, cross-sectional prediction. Tell me those attributes of the firm. I tell you what CDS should be. This is built based on those attributes for those with a CDS. Got it? And so this is a very big data set, you think about it, right? Okay, so potential is built, the model is built on smaller data set, which is pretty big already, because I was telling you that about 140 some observations. Why? Because every company with CDS, there are different tenors, 1 year term, 2 year terms, 3 year terms, and over different points of time in history. I can do daily, weekly, here case I do monthly. So every month I take a snapshot. It's still very long, 15 years, right? And so many companies, so many tenors. So it's actually 140 some thousand observations, okay, with 400 some variables. Okay, oh, it's done. Yeah, okay. So I convince you that can be done, right? So you don't even need to write the software here. So you open, so you can just look at cross-validation result. It's worthwhile seeing it. Okay, so it tells you pick 78 variables with all the interaction terms, including intercept as a potential one. In the end, you actually chose intercept. Intercept is not insertion, it's chosen. Okay, and you can see that I have chosen 6 regressors, and that's based on cross-validation results. Okay, these are 3-4 cross-validation built into programs. Okay, if you want to change that, this program had to go back to change that Julia. Okay, the user don't really need. Okay, so that's the sort of situation we're talking about. So let me go back to my talk. So I already touched upon that CDS data. So let me sort of tell you one thing, okay? Now this is a graph, you know, something called bond yield spread, and I may need to explain. You take a, say, IBM bond, what will be the interest or yield on the bond compared to US Treasury? That's called yield spread. Of course, you expect IBM to pay higher interest, right? Versus US Treasury, that yield spread. That yield spread, in theory, should be CDS premium. In reality, of course, there are noises. So this is a plot people have produced. This is from the journal. Right? It's a CDS premium versus yield spread. They are not zero. Okay. The difference between these two, in theory, is supposed to, in reality, are not. But this yield spread can explain 80% of CDS variation. So it's very good. Theoretically, it's identical, right? In practice, 80% R squared. Why that's important? What I'm saying is, even you know bond yield, you can get 80% R squared in predicting CDS. The thing is that regression is established, but it's useless. Why? Because you do not, when you don't have a CDS, you don't have a bond either. So the purpose you want to do the prediction for those without CDS are those ones without bond anyway. Okay? So you have that regression relationship for scientific study or academic study, but it's not practical, because you don't have right-hand side. So what I'm going to do is a bunch of variables on the right-hand side. They are not tied to CDS in availability, but relationship-wise they are. Okay? So that's the point of this. So there are a bunch of variables. I'm going to skip all this. Okay, there are a lot of CDS here, about 300 some US firms and from 21 economies. There's 405 companies altogether. There are many observations. These are USD denominated, also Euro denominated. Okay, I'm doing USD denominated. So anyway, yeah, different tenors. So the sample is very balanced. Okay. Okay. The other, there's one technical thing I probably don't want to explain because it's complicated for those who do not know finance. Okay. Anyway, it's all these things, standard financial is being considered. What I want to mention is this: if you do individual R squared, remember that I have 29 experimental variables before interaction terms. Yeah. And each individual one has an experimental power, varies. One single variable called actuarial spread, that's produced by the NUS team. You know, I lead a team at NUS Risk Management Institute to produce the world's largest corporate default prediction system. And our system is daily updated for every exchange traded company. The team now is about 45 people. Okay, among all the output we have, it's called actuarial spread we generate. It's daily updated for every exchange traded company in the world. And this turned out to be highly informative about just alone, one variable alone is about 50% R squared. And that is a variable for every exchange traded company. On the left-hand side, there are only 500 CDS. You see the difference now? It's about 35,000, this is 5. So the right-hand side is a variable and being daily updated. It's completely, user completely have a free access to it. So that is one of the variables I will be using, okay, among many other variables. Then we create, you know, this is just decreasing order. You can see that many have a very small individual R squared. But even this one, okay, is sub. Whether the debt reference to is a subordinate debt itself has only 92 observations. Turns out individual has no R squared, very tiny R squared. But in combination become very important. So let me just make a very side comment. Traditional people use the greedy search technique. You can see that it's a very bad technique, right? Because in combination, that's what it is. A multi-dimensional problem is much more complicated. So if I do this, you know, search using the technique I was referring to, you know, I actually end up select 24 regressor out of 442. Okay, these are the choice. And many of these has a, you know, this actually has a meaning. Of course, I have no time to talk about it. So the R squared is almost 82%. The in and out sample are very stable, okay? In the paper was a search by BIC. Cross-validation take a longer time because you have to do that search. Say 3-4 cross-validation, literally 3 times, right? The computing time. Okay, so these are the plots, you know. What happened is this is the proxy we have. This is a proxy I generate by regression, and I classify sample into various categories to see the performance, whether they are specific, good performance in some category and not in other category. All across the board, very stable, you see that. Okay, so this kind of regression can have very high R-square and highly stable. You know, even beat the one which is bound yield. Bound yield spread. Okay, anyway, so this is sort of big data in action. Right? I guess I'm running out of my time. So I can take some questions.
So I think you were saying that once you do this kind of SMC method, when you're
It's density tempered SMC.
so when you're tempering parameters, say 1, you would look at sort of the max of among all your particles, say?
No, I don't. You know, what I want to do is when I reach delta equals 1,
Yeah.
I see it. Because in between it's not a target
So,
function.
yeah, so when delta is 1, you would look at the maximal.
That's
the
right.
point, the maximal
That's right.
value,
Because I cannot use any average because these are discrete.
Sure, yeah. So my question is really that something that people tend to do in this setup is to do annealing, so you would potentially even, select a delta that's much higher.
Yeah, you could do this. It's called data cloning in this context. I use it a lot, but not in this context because this is discrete.
Right, so you don't think that would help?
No. Because you know what? There are 2 ways to fill in to get accuracy. One way is use a K4 duplication. So 100 become 1,000 become 2,000 become 5,000. You can fill in. And the other one is raised to the power 2, 4, and all that. And actually, in terms of rate, are identical. Square root of K. It's a Monte Carlo. You know, you can prove that by powering these things square. It will eventually become normal distribution.
Ah, yeah, I can see why that.
Yeah, okay. And the rate is just exactly 1 over. Okay, you can shrink basically you make a density function, or in this case a probability function, but it's discrete, so remember. Okay, it's not very good things to do. So in many contexts when it's continuous, data cloning, that's how we call it. Data cloning is more efficient. Because what data cloning will do is actually have a paper on my website you're interested called SMC square technique. Because data cloning is a way to get rid of multimodality. If I have a multimodal problem, I keep on filling into 1,000 to 10,000. It's still multimodal. If I power this, the higher peak will dominate the lower peak, eventually disappear. So there's a normality result there, but not in terms of rate. Rate, you can prove that both are square root of n. Okay? But computationally, if it's continuous, it does have advantage to do that. Okay.
Have you tried a deep sampler to choose, to select some use and deselect some?
No, there's no need here, right? Because there is a natural independent sampler. Because it is a sample, just look at it, right?
Have you tried it?
No.
Because people use GIP samplers in similar problems where they try to decide which variables are important.
Yeah.
They seem to report quite good performances, but I understand that you're in an SMC context.
Yeah, but you see, you just think about it. What happened is I have a bunch of, say I have a 500 variable. Each one have a occurrence in 1,000 because they're multidimensional, say 10-dimensional. I can count their occurrence. So that give me a reason individually how come in. If I start to do anything jointly, it's very complicated in proposal and it's a density function. So I will bypass all those things because in the end it's about evaluation of that and generating of that. So the simplest way is to simulate by permutation actually, without correlation structures, independent, because that's easy calculation, and easy simulation, right? So I think there's one trick I realized. At some point I was stuck because I was trying to think about combination. And as I realized, well, why do I just think about over permutation? right? Because it's much easier to simulate. And any sort of fancy thing you start going in, may not pay off because this is a numerical intensive. Now there's also one thing, since you mentioned numerical things, I'm fully aware of that, very conscious of it. You think about this problem. It's critical at this point. It's critical at this point to think about these things. Yeah, it's this solution. In other words, if I give you a vector, a set of regressor, I immediately can compute a likely function, the density function. It turns out that, I used to think it's easy, not easy. Analytical easy, you compute it, it would be near singularity and all that, right? Okay, and the other thing is, it's taking a lot of time if dimension is high. So the computational, this can actually be dealt with very fast now, because all you have to do is just remember, don't use original observation, because you repeat it, you use sufficient statistics. Okay, that's one key. Okay, then you have to deal with the near singularity. Okay, but still there's a limit to how this is generalized to logit and other nonlinear form. For a while I was very discouraged. I thought there's no hope, because whenever I pick a combination, I need to be able to analytically solve the problem, or close to that analytical solution speed. Otherwise, it takes awfully long time. But it turns out I don't need to. I had just figured out a way I can deal with a nonlinear function even. Interesting, I'm not going to tell you now, okay? And it's actually completely doable. It's interesting, it's fascinating. It's much more stable, and it will even bypass singularity problem. So, one thing I learned from this exercise, when you have very concrete objective, this objective is a real life operational needs. It gives you extra incentive to do it. You just write a paper, I quit, because we really have a real need for it, And I start to say, I need to work on it. I never quit on this. But it's an interesting journey.
Thank you very much.
Thank you.